Physics tries to predict the future. For example, if you have been given an apple, the job of physics is to tell you the effects on the apple if certain forces are applied. For example, what would happen if the object was to fall from a tree, or what would happen if a push force was to be applied? The Schrodinger's equation is used to find the energy levels in a mechanical system, and the wave function gives the probability of finding the particle, meaning it predicts the future behavior of a dynamic system and the energy a particular molecule may possess, similar to the apple. But what does this actually mean? Erwin Schrödinger's wave equation follows the discovery of Hamilton, de Broglie, and Einstein, resulting in a time-dependent and independent equation, making it so interesting. Although there is no definite way to derive the Schrödinger's equation, there is a simple way to do it to understand its complexity and roots. So let's derive in simple terms the time-independent Schrödinger's equation. So to begin with, we know that the total energy is kinetic energy plus potential energy, which can also be written as half mv squared plus u. U is defined as the potential energy depending on where we happen to be. For example, it can be a gravitational field or perhaps an electrical field. Since P is equal to mv, we know that P squared is equal to m squared v squared. We have a wave which will take form of psi, and if we differentiate psi in terms of x holding x constant, differentiate a second time, recall that k equals p over h bar, as k is defined as 2 pi over lambda, and a final differentiation results in an important equation which can be added to the initial E equals p squared over 2m plus u, and equating both equations will lead to a time-independent Schrödinger's equation. We can also derive the time-dependent equation by reminding ourselves that E equals h bar omega, which is equal to hf, where h is the Planck's constant. This time will be differentiating psi in respect to t. So we can substitute E psi into the Schrödinger's equation, thus leading to the time-dependent equation. The time-independent equation is more commonly used. Throughout the whole equation, we have no representation of time, and it is only dependent on space, thus helping us pinpoint any wave at a given instance of time. We can also change various operators, resulting in different outcomes. A simultaneous operator will give us variations in the energy, and certain velocity operators will enable us to get variations in the velocity of molecules. Although quantum mechanics is a very complicated topic, these equations alone are elegant enough to be appreciated without any knowledge. The Schrödinger's equation is so special that it can also be applied to various other aspects of science, such as quantum mechanics, the no-cloning theorem, quantum teleportation, and many worlds interpretation. Arguably, the Schrödinger equation is one of the most beautiful equations in history and forms one of the pillars of our modern electronic technology. Quantum mechanics thus reveals a basic oneness of the universe.